There we go. All right, so let's pick up where we last left off then. We just got the dot products, and there's deliberately a dot here and here to represent the multiplication because it is a dot product. There are two types of multiplication. There's dot products and cross products. We will go into more detail on cross products in chapter 8. Dot products because it's represented by a dot, and cross because it's represented by a cross. Dot products are also called scalar products. Because it produces a scalar. Cross products are sometimes called vector products. Because they produce a vector. You would think so. Actually, from our point of view, yes. The purists would go, no, it's not a vector. It's called a pseudo-vector or an axial vector, but it looks and smells the same, so vector. Sometimes this is, I think more generally, it's called an inner product. And anyone want to take a guess what this one's called?
Outer.
Outer. But I tend to call them dot products and cross products. Now, the main difference between the two, besides this producing a scalar and this producing a vector, is that dot products cares about parallel. And cross products cares about perpendicular. And what I mean by that is when I'm doing a dot product, I'm multiplying how much of one vector is in the same direction as another vector. So if I have two vectors here, A and B, and I do a dot product, A dot B, I figure out how much of A is in the same direction as B. The math lingo is you do a projection, but how much of A is in the direction of B, and you multiply the length, that length right there, the part of A that's in the direction of B, times the length of B. That's what a dot product does. And the cross product, if I have A and B, try to keep the same. I figure how much of A is perpendicular to B, and I multiply the perpendicular parts. Now in 151 and 251, we'd get into the trig involved in it, but we're not going to here. We definitely don't need to do that for what we're doing over there. We'll get into slightly more detail actually in this chapter. There's another dot product that shows up, not just in what we're doing right there. Another dot product that shows up, and we'll talk a little bit more about dot products at that point. So, given this, if I take some vector A and I do a dot product with itself, what would that be? What would the answer be?
Zero?
Not 0. If I did a cross product with a vector with itself, it would be 0.
Square?
Do the whole thing.
A squared?
A squared. Because how much of vector A is in the same direction as itself? Well, all of it. So I multiply how much that is times A. So any vector times itself, dot product with itself, I should say. Any vector with a dot product with itself is just the magnitude squared. So if I do I hat dot I hat, what is that equal to?
That's square. That's square.
Well, what's the magnitude of I hat? As a reminder, it's called a unit vector. What's the magnitude of a unit vector? I think somebody just said it. Maybe I'm imagining things.
I said Newton.
Oh, no. The purpose of a unit vector is to indicate direction. The magnitude of a unit vector. And again, let me emphasize the word unit. What is the magnitude?
1.
Yes. So I hat dot I hat would be 1. I hat dot j hat would be remember that I hat and j hat are perpendicular to each other.
I had J hat.
Yes? Would be,
J.
nope. I have these two vectors that are perpendicular to each other. How much of I hat is in the direction of j hat?
0.
0. So the dot product would be
0. Oh, okay.
Yep. All right, so given this, primarily any vector dot product with itself gets the same thing. I do want to point out one other bit. If you flash back to math vocabulary, the commutative property. What is the commutative property? There's a commutative property of addition and a commutative property of multiplication. What does that mean?
Isn't that like whatever order you do it in doesn't matter?
Correct. 2 times 3 is the same as 3 times 2. The commutative property holds for dot products. It doesn't for cross products, but it does for dot products. And I'm just going to abbreviate it. The comprop holds. So j dot I and I dot j get you the same thing. A dot b, b dot a get you the exact same thing. And just a side note, for cross products, you get the negative value if you flip the order around. But we will definitely, chapter 8. All right, the other thing that I'd like you to recall, flash back on, is FOIL. Now, I know it's pretty traditional American. I don't know what you were taught. Were you,
Asian.
okay. You know what I mean when I say FOIL? Okay. Quick review, if I have A plus B times C plus D, multiplying binomials, multiply the first ones together, so I get AC, outer plus AB, inner plus BC plus last BD. Does this look like something you've never seen before in your life? Is there anyone who's look at this and goes, I have no idea what that is? I think I first saw it in Algebra 1. I don't know what it's taught now. All right. Suppose I have A plus B times A minus B. What do I get?
A squared plus B squared,
Nope.
or minus B squared.
Yes. You multiply the first ones, you get a times a, which is a squared. Multiply the outer ones, you get negative ab. Multiply the inner ones, you get positive ab. And the reason I can flip it around is because commutative property holds. And then multiply last, negative b squared. So I get a squared minus b squared. And with that absolutely rousing refresher, we can now come back over here. All right, questions before we actually get back to the physics? And I'm really curious about the Google automatic subtitles. How well they're gonna do when everything's muffled in just a little bit. I haven't checked. All right, so over here, I threw in one intermediate step from what we did yesterday. But over here, the times cancel out. Times cancel out. That dividing by 2 is the same as multiplying by a half. It's just a constant. Since it's not a vector, I can just factor that out. And so I end up with 1/2 mass of object A times VFA, that's really not much better, minus VIA, dot product VFA plus VIA. So all I've done is just take the left-hand side here, brought the 2 in front, made it a half, and then I just have this dot product with this. And now we FOIL. So I have 1/2 mass of A, VFA dot VFA. So just first outer plus VFA dot VIA. Inner minus VIA dot VFA. And then last, minus VIA dot VIA. It does simplify down in the end. These right here, not what I wanted to pick up. These right here are the same thing. I have, since commutative property holds, I can just flip the order around and it's the same thing and it just goes away. This right here, I have a vector dot product with itself, so this becomes 1/2 MA times VFA squared minus VIA squared. The vector symbols have disappeared on purpose because it is a dot product or a scalar product. On the right-hand side, I have negative 1/2 MB times VFB squared minus VIB squared. We are getting close. I'm going to distribute here. 1/2 MA VFA squared minus 1/2 MA VIA squared equals, so just multiply this times that, and then times that. Now I take that, distribute. Negative 1/2 MB VFB squared plus, because the negative signs, 1/2 MB VIB squared. You thought it would have happened sooner, but at this point, physicists get tired and they said, man, 1/2 MV squared shows up again and again. Let's just make up something for it. We haven't used K in a while, let's just use K. Capital K. So this is K final of A minus K initial of A. So K is equal to 1/2 MV squared, and that's a V, equals negative K final B plus K K initial V. Almost close to the punchline. At this point, the physicists decided, you know what, let's get all the final terms on one side and all the initial terms on another, so let's just bring this over to that side and this over to this side. Well, whenever you bring a term from one side with an equal sign to the other, you have to either subtract or add. So I'm going to add KIA to both sides, and I'm going to add KFB to both sides. And what I'm left with is this KFA plus KFB equals KIA plus KIB. And at this point, the physicist's heart gets all a twitter. As you recognize, what we have here is, I have this thing called K, 1/2 mv squared, and all the final terms add together to give me the exact same thing as all the initial terms added together. This is known as a conservation law. So now some vocabulary. This K here has a name. It deals with movement because V, if V is 0, then K is 0. But it does deal with movement, so they gave this K for kinetic energy. The one formula I expect you to have memorized, as in 30 years from now, if I run into you, I should be able to ask you, what's the formula for kinetic energy? And you should know it. So let's practice a little unison here. I'm about to ask, what's the formula for kinetic energy? And then in unison, you are to reply 1/2 mv squared. Now, normally I can see mouths move, but I'm going to have to look for vibrations in the mask. Right? Some people are still writing down. I want to make sure that they're part of this too. Occasionally I'll have a student go 1/2 times mass times speed squared. No, I want 1/2 mv squared. That's the response. All right, so here we go. What's the formula for kinetic energy?
1/2 mv squared.
Almost like a chorus of angels. Let's try it one more time. What's the formula for kinetic energy?
1/2 mv squared.
I expected more enthusiasm the second time around. Well, you'll be asked this several times throughout the course, and you're going to nail it with great enthusiasm. Now, another vocab word. This right here, this force times displacement with a dot product, this is known as work. And one of the reasons I don't use capital W for weight, because I use capital W for work. Going through that. This will go away. Okay. Depending on how you want to look at it, work could be considered just a math formula that's over there. Work also is a way that energy gets changed from one form to another, so we'll talk about that in just a moment. So if I have a box here, and it is being pushed to the right, say a 5 Newton force, and this is a 3 kilogram box, and it is pushed 2 meters, or that a force is applied over that 2 meters. Positive work or gut feeling. Is this positive work being done if I have a box and I push it the 2 meters in the direction it's going? But, yeah, and that's positive work because the force and the displacement are in the same direction. So my displacement, that would be my delta x. There's my force. So the work done here is, well, 5 newtons times 2 meters, both in the same direction, so that would be 10 Newton meters. Because I multiplied newtons times meters. However, Newton meters is too much for physicists to write, so they came up with a one-word unit, 10 joules. This J right here is a joule. So we have our second derived unit. I'll put it up over here. We have 1 Newton is defined as 1 kilogram meter per second squared. And now we have 1 joule, which is defined as 1 Newton meter, or 1 kilogram meter squared per second squared. Well, it's very similar to a Newton, except we do have that extra meter there. So on a quiz or test, if you're dealing with work or energy, you can put it in Newton meters or joules, either one is correct. Now, when we did this derivation right here, we had these two objects that are hitting each other, and they exert a force on one another during this collision. But we ended up with what looked like a conservation law, that the total kinetic energy beforehand equals the total afterwards, except that doesn't quite always work. I take this pen right here. From our point of view, what is the kinetic energy of this pen? Why? Right, okay. So the kinetic energy is 0. If I let go, did the kinetic energy stay 0? Okay. So physicists, still trying to push in their conservation laws, go, wait a second, we got to come up with another type of energy. And they did. Matter of fact, there's 3 basic types of energy. It's classical physics when they're doing all this stuff. And they basically realize that all objects have 3 things. All objects have a speed. Now sometimes the speed is 0, but it is still a speed. They have a position. And they have mass. Again, classical physics. Speed is related to the kinetic energy. The symbol being a capital K. Position is related to what's known as potential energy. And the symbol that I use for potential energy is a capital U. So just please make note of that. I think Hewitt does, either writes out potential energy or does capital P, capital E. And mass is related to what is known as rest energy. Technically, rest mass. I should write rest mass in there. and just E sub R for rest energy. I want to spend a little time on rest energy, not a whole lot, but a little bit of time. So what is rest mass? Well, every time that you use the triple beam balances, you are finding the rest mass. The rest mass is the mass of an object when it is at rest relative to you. And the reason why there's the distinction there is you can also find masses, the value of a mass through collisions. You don't have to find mass by putting them onto balance, which is helpful because if you're trying to find the mass of an element of a, let's say, a mass of an electron, it's helpful not to have to put it on top of a balance because electrons are so tiny. So you do it through collisions. And so those are the cases where an object is, you're trying to find the mass of an object that is not moving at rest relative to you, or that is not at rest relative to you. All of you, I'm pretty sure, know the formula for rest energy. Although if I said, hey, what's the formula for rest energy? I suspect, if you're like the typical class, no one in here can tell me, but I can start you out. Ready? Because you're about to do this one in unison for a formula that I suspect none of you have heard before, that none of you think you know right now. Here we go. E equals, so it's kind of like back and forth there. I assume everyone else said it at the exact same time and it sounded only like two voices. That's how unison you work. Yes, the formula for rest energy. And you put a little zero down here to indicate rest mass, C squared. If you took a match and you found the exact mass of the match, and then you struck the match, collected all the ash and smoke that comes off of it, and then take all that ash and smoke and the particles in the smoke, and then the match itself, and you put it, and you find the mass of that, there's going to be a small difference in mass. And that small difference in mass was the rest energy that got converted into, well, in essence, kinetic energy. It got converted into radiation. There's a small loss in mass, and that was converted into energy. That's the essence of the atomic bomb, is you take mass and convert it, or a hydrogen bomb. You take mass, convert it into radiation usually. All right. So what they eventually came up with is not that kinetic energy is conserved, but that total energy is conserved. E initial equals E final. This is conservation of energy. And an ever-fading marker. That the total energy initial is equal to the total energy final. So as the marker fell, it gained kinetic energy, but as it gained kinetic energy, it had to lose other types of energy. It lost potential energy. Or the potential energy got converted into kinetic energy because work was being done. So work is the mechanism for transferring energy from one type into another. That's the conceptual definition of work. So if I take this box here, I'm going to push on it. After I stop pushing on it, does it have kinetic energy? So I'm talking immediately as soon as my hand leaves it, does it have kinetic energy? You said no and yes. It's one of those.
Yes. Yes.
All right. But does it have kinetic energy now?
No.
All right. So where did the energy go? Energy is supposed to be conserved. Physicists place a lot of stock in this, but it had kinetic energy, now it doesn't have any. And I will tell you, the potential energy did not change. Where did it go?
It stopped when the box stopped.
But it had to go somewhere, because we're making the claim that the total energy stays the same. No. If that were true, that means the box has more mass now than it did when it started. So it looks from this point of view that the box lost energy, but it went somewhere. Well, think about what's interacting with the box. The energy went into the table. The table, at least slightly warmer. When you rub your hands together, you're converting energy from one hand into the other. You're basically, well, converting sort of some large-scale kinetic energy into kinetic energies at the surface. The particles in the table will be moving slightly faster. So we need to somehow differentiate. I say need, I mean all of you know this, of course. Your life will not be complete without this knowledge. We all need, so we need some way of actually talking about energy that's being transferred from kinetic to potential, or potential to kinetic in the same object, and energy that's being transferred to something else. And of course, we have a way. Conservative work and non-conservative work. They got really clever with the second name. Conservative work is done by conservative forces because it's just force times displacement. So this has conservative forces. Someone take a wild guess what non-conservative work is created by.
Non-conservative forces.
Absolutely. There is an official definition. It is calculus-based. I'm not going to give that to you unless there's a desperate, if you want to know, I can tell you afterwards. Instead, I'm going to give you